We're delighted today to have Caroline Beghein to talk to us. Caroline did her bachelor's in Liège in Belgium in physics and got a master's at IPGP in France, and then did her Ph.D. at Utrecht in the Netherlands. She did postdocs at MIT and at Arizona State, and since 2007 has been an assistant professor at UCLA. Caroline has very diverse interests in seismology. She is interested in global deep earth geophysics as well as regional tomography of the lithosphere and astenosphere. And I think one of the things that characterizes her work is she goes all the way from the core to the top and top of the lithosphere. She's going to talk about some interesting work today, and some of it probably is related to a paper that just came out in Science Express last week. So if you want to catch up on what you're hearing today, just open up Science Express. Today she's going to talk to us about new constraints on mantle dynamics and ocean plate formation from seismic anisotropy. Caroline?
Okay, is this working? No? Okay. How did you get this one? I thought you did. Okay, can everybody have? Yes, it's on. Oh. Well, thank you for inviting me to present our research here. I'm not going to talk about the core today, and so I wish I could, but there's not enough time. And I basically picked two subjects that are related, and you'll see how during my talk. And both of those subjects touch on mantle dynamic and how it relates to plate tectonic motion. And I want to acknowledge my collaborators. So these are the most recent people who have worked with me on these specific topics. We have my two graduate students at UCLA, Kei-Ching and Zheng, and also Nicholas Schmer, who we all know from having been here. And so to give you a brief outline, I'm going to start talking about my motivation for studying seismic anisotropy and put it in a general big question context, big science question context. And then I'll show you what kind of data and method I've been using to investigate these questions. And then I'll move on to the results. And well, first I will show you a global model for the entire planet of seismic anisotropy. And I will focus on the mantle transition zone because we have some very interesting and unexpected results. Then we will basically zoom in onto the upper mantle beneath the Pacific Ocean and look at how oceanic plates relate to seismic anisotropy. And I'll have some conclusions. So first, motivations for studying seismic anisotropy. So we all know that the Earth is different from other planets because we have active plate tectonics. And these tectonic motions at the surface are related to convection inside the mantle. And there are lots of open questions that we still don't have a clear answer for. For instance, we do not know what drives mantle convection. It's probably mostly thermal, driven by temperature, but there's probably also some chemical compositional effects that may drive the convection. Is there coupling between the plate and the deeper mantle? We know there's some hints that in some location, near subduction zones, there might be decoupling. The very deep mantle, lowermost mantle over here, does deform. There's some localized regional evidence for deformation from seismic anisotropy, but do we actually have a large-scale signal that we can detect? And what about the core in all this? We do not have very strong constraints, very definite constraints on the density jump at the inner core boundary, which is an important constraint to have in terms of the evolution of the core. How fast has it been growing? When did it actually form? And also the velocity of shear waves inside the inner core. There's a big discrepancy between estimates from seismology and from mineral physics. So these are the kind of subjects I'm interested in. And more recently, I've been focusing on this topic. What is the style of mantle convection? There's basically two n-member models. One is a model shown on the left, where we would have layered convection in the mantle. This is generally favored by mantle geochemists. This would mean that we have, well, that's because the mantle geochemists need to have lower mantle reservoir chemical heterogeneities. This would imply some decoupling between the upper and the lower mantle, which would mean that we would probably have a mid-mantle boundary layer and less efficient cooling of the planet as a whole. While on the other hand, we have a whole mantle convection model where we have basically big convection cells going from the core mantle boundary to the surface, which would be a much more efficient way of cooling the planet. And we would have a much more homogeneized mantle. This is mostly favored by geophysical arguments in general. And the consequences, these two end-member models, also is that this affects our knowledge of the temperature profile in the Earth. On the right, we would have, this is typically what we see in textbooks in terms of geotherm, but that's for whole mantle convection. Well, if we had a mid-mantle boundary, the geotherm would look different. Now, the mantle transition zone could play a very important role in trying to answer these questions. The mantle transition zone is located between 410 and 660 kilometers depth. It's basically the bottom of the upper mantle. And it has been known from seismology for several decades, and it is characterized by a jump in seismic wave velocities. They just suddenly increase at 410 and 660 kilometers depth. And it's attributed mainly to a phase change of olivine because of pressure change. But the mantle transition zone has also been proposed as a potential water reservoir. So the solubility of the water solubility of mantle transition zone minerals is actually higher than what we have above or below. And so if we have subducting plates transporting water down into the mantle, it is possible that some of the water contained in the rocks could end up in the transition zone. And then, in relation to the style of mantle convection, the mantle transition zone could be this mid-mantle boundary layer that could have horizontal flow if we had several convection or layered convection. So basically constraining mantle deformation inside the transition zone and above and below is really important to have a better understanding of how the mantle convects and also to get a better understanding of the history of plate tectonics. So my tool of choice has been to look at seismic anisotropy. So as you probably all know, most of you having had several people working on this type of topic here, seismic anisotropy is the dependence of seismic wave speed with the direction of propagation or the direction of polarization. So if you had, for instance, a shear wave entering an anisotropic medium, the two directions of polarization would split and travel at different speed, and then you would measure a delay time between the two directions at a seismic station, and that's a direct evidence that the wave went through an anisotropic medium. That's called shear wave splitting. The only problem, which is actually a big problem, is that shear wave splitting is basically integrated along the whole path of the wave, and so there is no real depth constraint as to where the anisotropy is coming from in the mantle. Seismic anisotropy in the upper mantle is thought to be mostly caused by the preferred alignment of olivine crystals. So when they undergo deformation. So if they're submitted to shear, we can see in the laboratory that randomly oriented crystals will end up aligned mostly with the direction of flow, basically. And so this is why we usually take the fast direction for seismic waves as evidence for the direction of active mantle flow. Now, there's some cases where it does not work. We know, for instance, if the olivine is hydrous, we can have actually a 90-degree relation, but in most of the mantle, the scale at which, the scale I'm looking at, we can assume that in the upper mantle, this relation is generally correct. So where is seismic anisotropy inside the Earth? We have a lot of evidence of seismic anisotropy in the uppermost mantle, in the crust, in the mantle lithosphere, in the asthenosphere, basically in the top 200, 250 kilometers. In the lowermost mantle, the lower prime layer, and in the inner core. And anywhere in between, in the mantle, it's actually unclear because the seismic data tends to lose resolution at this depth. And so it's been a challenge, and if you look at these two models, so these are models from two groups of radial anisotropy, which basically measures the difference between the speed of wave in the vertical and horizontal direction. And so if we look at the model on the left, we have depth on the vertical axis and then the strength of the anisotropy on the horizontal axis. And if you are to the right of the vertical line, it means that the horizontal direction is faster than the vertical direction and the other way around on the other side. So we see these two models, they both agree, and all models agree, that in the top 200 kilometers depth of the mantle, horizontally polarized shear waves are faster than vertically polarized shear waves. So basically the horizontal direction is faster than the vertical direction, and the strength of the anisotropy decreases with depth. Then as soon as we reach 250 kilometers or so, there's huge discrepancies between the models. This is a perfect example. This is a model from the Berkeley group showing that in the transition zone is the horizontal direction that is faster, and in this model from the Utrecht group, the vertical direction is faster. So completely opposite results. And in my own work that I'd done in my Ph.D., we had tried basically a forward modeling technique to try to sample all the models possible, compare with the data. And we had obtained this, and I'm going to explain what this is. We have depth on the vertical axis, strength of the anisotropy on the horizontal axis. And the color scale you see, you can basically imagine that there are probability density functions, so distributions of models, where white is the most likely value, the most likely models. We have a probability of 1 of having this value at this depth. And as we go toward red and yellow, we are going toward less and less likely values. So we see that in the transition zone, which is shown by the arrow, which is just this layer, the most likely value is a slight preference for vertically fast shear waves, but the uncertainty was large, very large. So radial anisotropy, even on average in one dimension, is really hard to constrain in the transition zone. It's also true in 3 dimensions. There are several models that are trying to map the lateral changes in radial anisotropy at different depths. And we have here 2 models from Harvard, from Berkeley. There are strong differences between the 2 models at 500 kilometers depth, so inside the transition zone. And then this one here is something I had obtained during my PhD. That's, so one thing I have to specify is that the color scale is actually reversed. I had used a different convention. So where it's red here, red should be blue here. But basically it's a very, very different model. And I had estimated uncertainties, and the value of the uncertainties is actually larger than the mean value of the model itself. So again, radial anisotropy in the transition zone is not well constrained at all. Now there's another type of anisotropy. It's called Azimuthal Anisotropy, which is basically, if you're in a horizontal plane, is which is the fast direction for seismic waves. Is it in this direction or in this direction, and so on. And we know it's present in the, in the upper mantle. We have lots of evidence for it, some small variations between the models, but not too bad. And then in the transition zone until last year, we only had this estimate from Trump and Van Heijs in 2002, where they had they were not trying to get a 3D model of anisotropy, they were just trying to see if their data was compatible with the presence of anisotropy in the transition zone. The answer was yes, and they had mapped it as this, but this wasn't meant to be a best fitting model. And they were also using data that are actually not very sensitive to the type of anisotropy they were trying to map. And so because we wanted to know more about the presence of anisotropy in the transition zone, we basically tried to attack the problem with a different data set. And so the type of data I've been using for this are the surface waves. So surface waves, shown here on the seismogram, arrive after the first P wave and the shear waves. They have periods of between a few seconds to a few hundreds of seconds. And we have two types of surface waves, Rayleigh waves as shown here on the left and Love waves on the right. And they have orthogonal type of motion, particle motion. They have the nice property that they are dispersive, which means that at different periods they are sensitive to different depth in the Earth, and so they travel at different speeds. And for instance, the Rayleigh wave at 35 seconds of period are mostly sensitive to the top 150 kilometers of the mantle, while if you increase the period to 175 or 250 seconds, you see the sensitivity gets to greater depth. And there is a nice linear relationship between the phase velocity of the surface wave at specific period and the elastic parameters that describe the structure of the Earth. It's just a simple depth integral weighted by the sensitivity kernels that are basically these curves that we can calculate with a reference model. So we can use this type of relationship, measure the speed of these waves in the frequency domain to and invert this relationship to get the elastic parameters inside the Earth. Now, the surface waves I just described are called the fundamental mode surface waves. They're the most commonly used, but there are also higher mode surface waves. And these are basically the wiggles you would see in a seismogram. So this is a real seismogram, this is a synthetic seismogram. The big signal you see here are the fundamental mode surface waves. But then before that, we have all these wiggles that are the higher modes. And if you were to decompose the different modes, you would see, so that you may notice the different scales. So this is divided by a factor of 25 because the signal is much larger for the fundamental modes. And then we get to a smaller and smaller signal. But you have the fundamental mode here, the first overtone arriving a little earlier, the second overtone earlier, third, fourth, and so on. And so they arrive slightly earlier as we go toward higher modes because they're actually sensitive to deeper and deeper structure in the Earth. And they have the nice property that they are also dispersive. So we can use a similar relationship between the phase velocity measurements and to get the structure of the Earth. Now I have done measurements of fundamental mode surface waves, not for this study, but I've made them. Measuring the higher modes is actually tricky because if we go back one slide, if I can, you will see that some of them arrive very close to each other in time, so that's tricky to separate. The Utrecht group had actually managed to develop a technique that allowed them to more confidently assess the phase velocity of these different modes. And they managed to make measurements of Rayleigh wave and Love wave higher modes over the entire planet using seismic stations all over the globe and earthquakes all over the globe. And so they made this data available to us, and well, I took advantage of it. This figure shows the sensitivity of these two types of surface waves, of higher modes, to structure in the Earth. So on the left, we have the sensitivity of Rayleigh wave to the Azimuthal Anisotropy of vertically polarized shear wave. So it's a shear wave that would, if it traveled from left to right, would be polarized like this. And so you see we have depth going down to about 1400 kilometers depth here. The fundamental mode surface waves shown in gray are sensitive mostly to the top 200 kilometers. But if you add the higher modes, the first, second in yellow, and so on, you see you get sensitivity to larger and larger depth. And nicely, we have a pretty good sensitivity in the transition zone. Now the Love waves they measured So they managed to measure the fundamental modes, also sensitive to the top 150 kilometers, and the higher modes that provide sensitivity to the transition zone and slightly deeper. And so these love waves can give constraint on the elastic parameters that control the anisotropy of horizontally polarized shear waves. So a wave traveling from left to right would be polarized like this. So with their global measurements of phase velocities for higher modes, the Utrecht group basically they determined the anisotropy of these Rayleigh and love wave in the frequency domain. And so this is a second overtone Rayleigh wave at 50 seconds period. And you see the black sticks basically represent the fast direction of propagation for these Rayleigh waves. And again, there is a nice relationship between the phase velocity measurement, or even the anisotropy in the frequency domain, to the elastic parameters that control the anisotropy in the spatial domain. So we can calculate the sensitivity kernels, which I just showed, measure the phase velocity and the anisotropy of the phase velocity, and invert this type of relationship to get a three-dimensional model of azimuthal anisotropy. If you invert the Rayleigh wave, you get azimuthal anisotropy for the vertically polarized shear waves, and if you invert the love wave, you get anisotropy for the horizontally polarized shear wave. And so that's basically what we did. And so from this global data set, we obtained a global model of azimuthal anisotropy. I'm going to show 3 slices at 3 different depths. So this is our model at 150 kilometers depth in the mantle. So you see the delimitation of the tectonic plates in white, continents delineated by black lines, and the red sticks basically represent our model. So they represent which direction the vertically polarized shear waves travel faster. This is obtained from Rayleigh wave inversion, by the way. And the length of the sticks, also the background gray color, represent the strength of the anisotropy. So you see we have a pretty strong signal in a big chunk of the Pacific at 150 kilometers depth, slightly lower here, but so there's lots of variations. There's some places that are strong, some places are less strong, and so on. But this type of model was, this model at this depth was nothing really new. People have obtained similar results before. What was new is that we were able to go deeper. And so if we go deeper, look at what we have at 300 kilometers depth, the signal is relatively different from what we had at shallower depth. There's some location where the fast direction is similar. If I go back and forth a couple of times, maybe, okay, 150 and then 300. There's definitely a change, an overall change in the fast direction of seismic waves. And then we were able to go deeper because we have sensitivity to the transition zone, and then again we have some changes. Not everywhere, but some changes. And inside the transition zone, there are some places where we actually have a significant signal, almost 3% of anisotropy in some regions, about 2% here and here. So it seems like we do have evidence that there is azimuthal anisotropy in the transition zone. But then I was intrigued by the change in the fast direction that seemed to occur at these different depths. And because it's difficult to look at maps and compare them, we tried to be a little more quantitative. And so we basically averaged the model amplitude over all latitude and longitude and look at what we had on average as a function of depth. And so this is what we got. So the vertical axis is the depth down to 1,000 kilometers depth. The amplitude here on the left is the amplitude, the strength of the azimuthal anisotropy. Red is our model, and blue and yellow are 2 other models, an older one in blue and a more recent one in yellow. And so if we focus just on the left panel for now, we see that we have several peaks in the top 200 kilometers that we don't see in the other models, but the amplitude, and if you were to compare the maps, which I don't have here, they actually look very similar. And so we have about 2% of azimuthal anisotropy on average at 150 kilometers depth. Then as you go to larger depth, the amplitude decreases. And one thing that was not seen before, definitely not with this model, is that the anisotropy re-increases at 300 kilometers depth. And then it decreases again, goes through a minimum, and then re-increases inside the transition zone, and then decreases another minimum, and re-increases slightly. So it looks like we have the several minima and maxima in the amplitude. There's a minima here at 100 kilometers depth. When we look at the very shallow mantle, it's better to look at different tectonics regions, which I'll do in the second part of my talk. Then we have, on average, a minimum at 250 kilometers, or more or less, and a minimum, which was very interesting, at 410 kilometers and 670, which is roughly where we have phase changes. That's the boundaries of the transition zone. We also looked at how the phase direction of the seismic wave changed with depth overall, instead of looking point by point. And so we calculated what we call a vertical autocorrelation function. All it means is that, so this is the correlation between different depths. So at this point, for instance, this is the correlation between the depth just above and just below within a certain window. So if we have a peak toward the left, toward low correlations, it means that there is a definitive change in the phase direction at that depth. So we had this minimum here that actually coincide with a minimum in amplitude. So a change in anisotropy direction and the minimum in amplitude, and so on. We have a few peaks here, including around 250 kilometers depth, where we have this minimum. And then, interestingly, at the top of the transition zone, there is a signal, a global signal, saying that the anisotropy changes at that depth. And then another signal slightly smaller at 670 kilometers depth, where we have a minimum there. There's a little dip here in the middle of the transition zone that we don't see clearly in the amplitude, but interestingly, this is also where there's a phase change going on. So this was unexpected and very interesting. So it seems like the transition zone boundaries are not just associated with jumping seismic velocity, but also with an overall change in the seismic anisotropy. Now, before I move on to what could cause this, so the model I just showed was obtained from Rayleigh waves, and we had this whole love wave data set that we inverted as well to get the anisotropy of horizontally polarized shear waves. And if we average the amplitude of this horizontally polarized shear wave model, we find also that we have a minimum in amplitude at the transition zone boundary, and then in this case we actually see a minimum in amplitude at about 500 kilometers depth. And then if we calculate also the autocorrelation function, the low correlation is less clear, but there's definitely a little dip here, a little dip here, and a little dip here. So it seems the uncertainty on the low wave data is larger, so we have to take that with a grain of salt. But it seems like for both vertically polarized shear waves and horizontally polarized shear waves at the transition zone boundary, we have a change in the amplitude and a change, or a minimum in the amplitude and a change in the phase direction of seismic waves. Another type of data which I've mentioned before that can detect seismic anisotropy is shear wave splitting. And with our model, we could actually forward model and predict shear wave splittings and compare with real data. Now, shear wave splitting and surface wave have very different vertical and horizontal resolution, so it's not that straightforward to compare. But one thing we could easily do was to calculate the splitting time over the globe and then calculate an histogram. So we have this here in yellow, our delay times, so the time difference between the arrival of the vertically polarized shear waves and the horizontally polarized shear waves. So shear wave splitting delay time data that have been actually, there's a database on Thornton Becker's website where we have shear wave splitting delay time over the whole globe. And you see here that it peaks at around 1 second or so. And in the top panel, you have this pink histogram that are prediction of delay time from another model, a model that used only the fundamental mode surface waves, so that had anisotropy only in the top 250 kilometers depth. And it had been a long-standing issue. This type of model with anisotropy only in the shallow mantle systematically underestimated the shear wave splitting delay time by a lot. But with our model, we calculated prediction of shear wave splitting delay time and plotted them in red, and we see that we are predicting delay times that are in much closer agreement to the actual data. So these are two independent data sets that seem to tell us that we do need to have anisotropy deeper in the mantle. That was a nice confirmation. Now, what could cause anisotropy in the transition zone? That's where this research was a little frustrating, because there's really not a lot of mineral physics data on this, so it was hard to compare. But because we found changes associated with at depth where we know we have phase changes of minerals, we think the anisotropy must be related somehow to the composition of the transition zone, to the minerals themselves, and so probably to a preferred orientation of these minerals with some deformation mechanism. Now, in the transition zone, we know that so olivine becomes Wadsleyite at around 410 kilometers depth. Then it transforms into Ringwoodite, and then we have another phase transition at 670 kilometers depth. Now, Wadsleyite is known to be anisotropic. There are single crystal measurement of anisotropy in Ringwoodite, in Wadsleyite. And Tomasi and I in 2004 also calculated an aggregate, a polycrystal of Wadsleyite, and showed that even if we put lots of crystals together, we still do get about 1% of anisotropy. So that's compatible with the type of value we got in the model. Now, in the lower part of the transition zone, that's definitely trickier. Ringwoodite, pretty much every single mineral physicist I've asked to say it is not anisotropic. There is no way it's anisotropic. There is this study by Kavner in 2003 that showed that she found an anisotropy signal in Ringwoodite, but it's highly controversial. So at this point, I don't know what to make of this. It's also possible that we can't actually differentiate in our model between the top and the bottom of the transition zone. Our current tests show that we can, but I'm skeptical, and we're actually doing some more, a little more fancier modeling, I would say, to get better estimates of uncertainties on the models. And so, if we have a change in anisotropy at the transition zone boundary, what does that mean in terms of mantle convection? To come back to the big question of layered versus whole mantle convection. If you assume that, like in most of the upper mantle, the fast direction for seismic waves reflects the direction of mantle flow, then it means that we have a change in mantle flow, that we have a very complex layered convection going on. However, again, because we do not have enough mineral physics data on anisotropy of these minerals, it's possible that there is not a simple relationship between fast seismic direction and direction of mantle flow. In the uppermost mantle, we know that water can yield a completely 90-degree relationship between the two, so it could also happen at larger depth. Also, the fact that we go through a phase transition, there is recrystallization, and this could erase the anisotropy signal, and it's possible that the anisotropy in the transition zone is very different than what we have above. We also don't know what the effect of melt or water possibly could do to anisotropy and its relation with seismic wave velocity. So basically, I don't have an answer whether we have layered convection or not yet. But this is one step, one more clue toward answering this question. And now I would like to take this model of vertically polarized shear wave anisotropy and zoom in toward the top of the mantle beneath the Pacific. And the reason to do that was, well, I started to look into the lithosphere-asthenosphere boundary. So the boundary between the lithosphere, so the plate tectonics, the plates that we have at the surface, and the asthenosphere below, which is much more deformable, we think, at least there's a lot of literature saying that it's probably a thermal boundary layer. That we have heat transport by conduction in the lithosphere, while we have advection in the asthenosphere. And if that's the case, half-space cooling models tell us that the thickness of the lithosphere should increase smoothly as it gets older, as with square root of time. And this seems to be supported by many tomographic models based on surface waves. And so this is one example showing the shear wave velocity as a function of depth and as a function of the age of the plate, increasing from left to right. We see around 100 to 150 kilometers depth near the ridge that we have a low velocity zone. And on top of that, we have a high velocity layer. And the thickness, if you take the black line, the thickness of the top layer seems to be increasing as the plate gets older, and it seems to be following a half-space cooling model prediction pretty nicely. So it seems pretty straightforward, except that there's another type of seismic data, or several types of seismic data, that have been used to try to investigate the lithosphere-asthenosphere boundary. Some of them are called receiver functions, but they basically are higher frequency data than the surface waves, and they allow to map discontinuities, jump in seismic wave velocity. This is just one study among many. And so basically these receiver functions can be modeled by a jump, a sharp drop in seismic velocity at depths that are usually associated with the lithosphere-asthenosphere boundary. And the issue is that because it's so sharp, it cannot be purely thermal. So there has to be a chemical component to that. And there's been a proposal that melt could be involved. And if we had, in this paper, it says that if we had melt aligned horizontally in the asthenosphere, it could yield to a sharp drop in wave velocity. And it could also explain the anisotropy, radial anisotropy we see at this depth. Now, Nick, a couple of years ago, also proposed that melt is probably present beneath upwellings, because when he maps this Gutenberg discontinuity, you see that the signal is strongly enhanced underneath hotspots, for instance. So melt is a possibility, and water is another possibility that has been proposed by Karato a few years ago, because the argument was that partial melt is difficult to get away from an upwelling, and if the lithosphere-asthenosphere boundary is chemical, it should be seen everywhere. So how do we get melt away from the upwellings? So he proposed that instead there is a sharp change in the water content of the rocks underneath the ridge, as we see here, that would yield to a hydrated asthenosphere and a dehydrated layer on top, the lithosphere, and therefore that would change the viscosity. So we had a higher viscosity plate on top due to dehydration. And this was supported by a study by Hirth and Kolstad in 1996, where they had done experimental work supporting this. Now to come back to Nick's study, he used a technique that allowed him to map the discontinuity over the entire plate, the entire Pacific plate. So many of the other techniques used to map this discontinuity only work underneath a seismic station, and we don't have a lot of seismic station in the ocean. So this technique was able to map the discontinuity, or to look for the discontinuity everywhere in the plate. But if you, I don't know if you can see from where you are, but all the gray squares, the gray symbols that you see here are places where you looked for it but couldn't detect it for sure. There are only a few places shown by the colored symbols where the Gutenberg discontinuity was detected. And again, this was stronger near upwellings like Hawaii or closer to the ridge. And it seemed from this figure that there is a slight increase in the depth of the discontinuity as you go toward all the plates. So red is relatively shallow discontinuity, around says, I don't know, 70 kilometers depth or so, and yellow is closer to 80 kilometers depth. So there might be a slight increase in the depth of the discontinuity. Now if you plot, as he did, the depth of these reflectors shown by the symbols with error bars as a function of crustal age, so increasing from left to right, you see that it's actually kind of difficult to see a systematic increase in the depth of the discontinuity with the plate age. And they do not obviously follow any half-space Collie model as shown by the black lines, solid lines, or any plate model, thermal model shown by the dotted lines. And so the fact that it's not observed everywhere and it's not clear that there's a systematic increase in the depth of the discontinuity with age made me wonder if the Gutenberg discontinuity was really the same thing as the lithosphere-asthenosphere boundary. So I decided to take our model and zoom in onto the Pacific upper mantle and try to see if we could find anything interesting. And so we have, so this is the Pacific plate. The background color is actually a shear wave velocity model that we obtained. We decided to look for shear wave velocities in addition to anisotropy. And so we have low shear wave velocity at 60 kilometers depth near ocean ridges as expected, and then the velocity of the wave increases as we get toward older plate age. The yellow arrows represent the direction of the absolute plate motion, so the direction in which the plate is moving. And the pink sticks represent our model. So fast direction for vertically polarized shear waves, and the length of the sticks is the strength of the anisotropy. I'm going to go through a few depths, and every time I have the ocean age here on the right, top right, where with young ocean near the ridge, and then we go toward older ocean like this. I also have a radial anisotropy model that tells you whether the vertical or horizontal direction is faster. I'm putting it here because we have it, but I will tell you right away that it's not resolved, so I'm not going to discuss it. There's definitely improvements to be made to this. But so we're going to focus mostly on this, and what we see at 60 kilometers depth is that the fast direction, one thing I forgot to mention before I move on, is so we have these black lines here that represent age contours, so 40 million years here, 80 million years, 120, and 160 over here. And these thin black lines that are probably not very visible from the end of the room, but these are fracture zones in the ocean floor. And so they can be used as a proxy for the paleo spreading direction of the ridge. So if you go back in time, this would be the direction the ridge was spreading when it was formed. So we see near the ridge at 60 kilometers depth that the fast direction for seismic wave aligns pretty well with both the absolute plate motion and the seafloor fracture zones. If you look in the middle of the plate here, the fast seismic direction doesn't match anything. It doesn't match the absolute plate motion, it doesn't match the paleo spreading direction, so really nothing really special. Then we go to 100 kilometers depth. You see that the model starts to change and the fast direction rotates, and we start to align. If you look more closely, you will see that we start to align with the paleo spreading direction over here, but not with the absolute plate motion. And then we go slightly deeper, where the seismic wave velocity is definitely more red, slower than on average. It's getting warmer basically. And you've seen that the fast direction for seismic wave has rotated even more, and we're getting closer to aligning with the absolute plate motion over most of the plate. And here here we start to align with the plate motion, not everywhere. But as we go to a larger depth, 200 kilometers depth, then there's an alignment that's pretty much all over the plate with the absolute plate motion. So this model, I mean, it was nice to get, but again, for the top 200 kilometers depth, people have looked at this before. It's not entirely new. What was new was that we wanted to look at how the anisotropy changed with depth, how it was stratified, and I wanted to compare with Nick's data. So I just happened to be at a conference last June when he was there, and we plotted his data on top of our model, and we found some very, very interesting things. So this is the amplitude of the anisotropy as a function of depth in the top 200 kilometers, and that's the ocean age. So in this case, it increases from right to left. So we're basically near the ridge here, going to the toward older ocean, and it's average over the entire plate. So it's not just one path. And the amplitude of the anisotropy is high is red, and low is blue and purple. So we see we have a very strong anisotropy here, and that corresponds to pretty much the middle of the plate, around 100, 150 kilometers depth. This has been seen with other type of radial of anisotropy, with radial anisotropy before, but not with this. But what was nice is that when we plotted Nick's data, which are the white symbols, and other people's data in black, on top of our model, we saw that it follows pretty nicely a minimum in amplitude. See this purple line, there's a minimum in amplitude. The solid black lines are half-space cooling models, and the gray lines are plate models. So it seems like the reflector data, they follow this amplitude minimum, but don't really follow clearly a half-space cooling model. And then we looked at how the phase direction aligned with the plate motion. So this is a similar cut, cross-section average over the whole plate, but purple and blue are basically where the fast seismic direction does not align with the plate motion. It could be anywhere, but not aligned. And then red and yellow are places where it does align pretty nicely. So we see that we clearly have a top layer where we have no good alignment with the plate motion, and a bottom layer where we align with the plate motion. And if you were to draw, fast-space cooling models, you see this, and there's a rough, the boundary between layer 1 and layer 2 is not clear-cut, but it follows roughly a half-space cooling model. And the reflector data clearly are inside the top layer. They're not following the boundary between the top and the bottom layer. Another way to look at this was to calculate the gradient of the fast seismic direction. So basically where it's red is a depth at which the phase direction changes really a lot, very quickly. And purple are depth where the phase direction just doesn't change with depth very much. And so we have here, you see a high gradient around 150 kilometers depth. That's basically this, the change from bad alignment with the plate motion to good alignment with the plate motion. But then interestingly is that inside this top layer we have another gradient, another high here in red, that's roughly at the same depth, constant depth. And the reflector data do align really nicely with this. So this was an unexpected result. So it does show that the Gutenberg discontinuity is not following the lithosphere-astenosphere boundary. If we assume that the top layer where the alignment with the plate motion is bad is the lithosphere, and the bottom layer where we have a good alignment with the plate motion is the astenosphere, which is a reasonable assumption. If the astenosphere is flowing, we should have a good alignment with the plate motion there. Then we see that these reflectors do not follow a half-space cooling model, and they do fall inside the top layer, not at the boundary between the two. Now we also had velocities, shear wave velocities, and if we look at a similar cut, we have in red low velocity zone and a higher velocity layer on top, where the boundary between the two layers follows pretty nicely a half-space cooling model, as expected and as seen before. And again, these reflectors are inside the top layer. The radial anisotropy, again, is shown here, but it's not resolved. However, all models so far have shown that at this depth we have horizontally polarized shear wave faster than vertically polarized shear waves, which would be an indication of horizontal flow from this type of anisotropy. So we also try to quantify this a little more than just visually, but it's again difficult because these are two different types of data, different vertical and horizontal resolution. But we did plot the depth at which the discontinuity has been observed versus a few features of the model. And here it was the depth at which we had a maximum in the gradient of the phase direction. And if it was a perfect match, it would be following the white line here, a one-on-one match. It's a cloud around it, but within uncertainties, if you try to draw a line a bit, to fit a line through these data, you get a slope of 0.9, so it's pretty close to having a slope of 1. We also plotted the depth of the discontinuity versus the largest gradient in the amplitude of the anisotropy, and a similar thing where we have a slope of around 1 if we fit a line through it. And then if we plot the depth of the discontinuity versus the depth of the largest gradient in the velocity, so from fast to slow, then we're clearly off. We're clearly below this 1-to-1 relation. And so we see that the gradient in the velocity is generally deeper than the discontinuity. And we have an age relationship. We see that in red for young oceanic plate, the gradient in the seismic wave is generally at shallower depth than if we go toward older plates in green and blue, where the largest gradient is deeper. And then again, radial anisotropy is shown here with huge uncertainties, and we can't really say anything of it. Not surprising. So what could cause this? So we have now evidence that the Gutenberg discontinuity is not the lithosphere-astenosphere boundary. That's inside the lithosphere, and it follows a change in the seismic anisotropy. So we tried to find an explanation. And we were inspired by work by Garrity et al. In '99, where it was based on the work by Hirsch and Kolstad, looking at dehydration at the ridge during melting. And they had proposed that the Gutenberg discontinuity was a chemical compositional boundary from wet to dry. When we have, so if we have material going up the ridge, we start to melt, and there would be dehydration that would yield to a discontinuity in viscosity and a chemical boundary. And so they assumed that this chemical boundary would be transported away from the ridge as it gets older. In this study, they had assumed that the Gutenberg discontinuity was the lithosphere-astenosphere boundary. Here we find that it's not the case, but we basically used the similar idea that we would have dehydration at the ridge forming a top dehydrated layer. And so if it's dehydrated and very viscous, the anisotropy, seismic anisotropy, would probably be weak and not aligned with any specific feature in the mantle. Well, if in dehydrated part of the mantle, it's more deformable, and so we would be able to align the crystals with the plate motion at the ridge, which would, as it gets older, become frozen in paleo spreading direction. But then on top of that process, we would have cooling of the plate, thermal cooling, defining a thermal lithosphere-astenosphere boundary. And so we would have these two processes going on at the same time, a chemical boundary inside a layer that's actually just purely thermal or mostly thermal. Now, melt is probably still present at some level. Nick's data showed an enhanced discontinuities near upwellings, and so it's possible that we do need melt beneath upwellings to still explain these discontinuity data. Melt may also affect the anisotropy in the astenosphere, but we would need these melt pockets to be aligned and tilted, not horizontal, to detect the type of anisotropy we modeled. So that's a little more difficult to imagine, but it's not completely impossible, I guess. And so that's basically concluding my talk. So to go through our main results, we've seen that by modeling Azimuthal Anisotropy, we're able to look at stratification in the mantle, to look at how it, to look at mantle flow as well. And we've seen that there is strong anisotropy in the top of the mantle, but also we were able to find anisotropy about 1% in the transition zone. And the more interesting result was that there is a change in anisotropy at the transition zone boundaries where we have phase changes. So this tells us something about the nature of the transition zone and the way the rocks deform at this depth. We just don't know what yet. It could indicate layered convection, although my gut feeling is that it's probably just something else, like precrystallization. It's also that the change in the anisotropy does not necessarily occur everywhere, even if we see a global signal. So there might be localized region where the effect of water or melt or something else possibly could affect that relationship. And then if we look at Azimuthal Anisotropy to look at the stratification of the upper mantle, we were able to find that the lithosphere-astenosphere boundary is consistent with a purely thermal model. And that the astenosphere is a low velocity zone with strong anisotropy that aligns with plate motion. But more importantly, we found that the Gutenberg discontinuity is not equivalent to the lithosphere-astenosphere boundary. That is actually inside an internal lithospheric boundary that is probably chemical origin, associated with a change in anisotropy, and that seems to have an origin at the ridge, and so it could possibly be due to dehydration at the ridge. And one thing I forgot to mention is that the fact that we have now associate the Gutenberg discontinuity with anisotropy could offer an explanation as to why the Gutenberg discontinuity is not observed everywhere in the Pacific plate. Because if we have anisotropy, then the detection of this discontinuity would strongly depend on the ratio of anisotropy between the two layers and the azimuth at which the wave arrives. So that's something probably to work on with Nick in the near future. Thank you for happy to answer questions.
Let me start with a couple questions. So, just in the last part of the talk, in the Pacific, you had this region where the fracture systems don't match the anisotropy, and does that region start where the Gutenberg discontinuity and the lithosphere boundary start to diverge in your sketch there?
Yeah, as far as we can resolve, it looks like above the Gutenberg discontinuity, the anisotropy does not align with anything, but below, it aligns first with the paleo-spreading direction, and then as you go deeper, it aligns with the absolute plate motion, current plate motion. So yeah, it seems to match, as far as we can tell at this point. We obviously would be better to get higher resolution vertically and horizontally, and that's hopefully we'll work on soon.
So if you compare a system like the Pacific, which is formed by a fast-spreading ridge with probably maybe higher anisotropy through that particular system, how would that compare to what you see in the Atlantic, where it's formed by a slower-spreading system?
Well, that's that's a good question.
I know it's not, you don't have the geometry of the earthquakes, and it's not quite as nice as
yeah, but that's something I'm interested in looking to, trying to compare the Atlantic and the Pacific in the future. I don't know what we'll get, and I don't know how our result will be able to, with the surface wave, how much resolution we can get. I also don't know how well Nick can look at the Gutenberg discontinuity in the Atlantic, for instance. That's
too slow.
Too slow.
100 million years.
Too slow, you said too slow?
Yeah, since the spreading rate is going so slowly, if you look at the distances between, say, 100-million-year-old plate
Yeah.
and zero, like new plate, they're pretty much right on top of each other for the seismic method we use to go look for the G's. So you can't really make that comparison between young and old to see if it's an age relationship.
Yeah. Might still be able to see change in anisotropy. I don't know. That would be an interesting thing to check.
Okay.
So I'm very interested as this change at the transition zones between the 410 and the 660 in terms of how to interpret. And one of the things for the 660 discontinuities also from the laboratory data we know possible there's a larger grain size change. Is that going to play a role in terms of
Yeah. So. Well, yeah, so grain size affects the relationship between, well, it affects whether we have diffusion creep or dislocation creep, right? So it affects the deformation mechanism inside the Earth. And so if we have diffusion creep, then it's a completely different, I mean, interpreting the anisotropy in terms of flow is something that, I don't know, I don't think anybody knows how to do. If it's if we still have dislocation creep, then lattice preferred orientation of crystal is still probably valid. So that would affect, depending on the grade sign, it may affect the interpretation of the model.
Yeah. But I mean, one thing is could dramatically changes the viscosity across the boundary. Is that's how that's going to cope?
Yeah, I would think that if there's a dramatic change in viscosity or in deformation mechanism, then it's probably going to affect the anisotropy, seismic anisotropy. So yes, that's a possibility, and this would be interesting.
Yeah.
I had a question regarding the layers of the dehydrated material. I would think that the dehydrated material will be further down instead of on the top.
I mean, this is what we found with the models. So with the surface wave model and with the reflector data, there's definitely something going on around 70 kilometers depth. And the Hirsch and Kohlstedt paper from laboratory experiments show that that's the same depth, 60 to 70 kilometers depth, where they expect to see a dramatic change in viscosity if there is dehydration. So I'm just reporting what we find, and comparing with results from experimental work, it seems that there's something going on at that depth. And interestingly, there's actually something going on at that depth under cratons that's been seen with similar studies of the North American craton, for instance. And whether it's the same thing or not, I don't know. I don't know how it could be the same thing, because I think they're supposed to be different rocks, but it's an interesting observation itself.
So going back to Faye's question a little bit, so if you have flow in the transition zone and it's introducing fabrics, I mean, these get reset, of course, across the recrystallization that takes place at the 410 and 660, but do you expect certain regions to have those fabrics that are formed in, say, subduction zones, uplines, and did you see any correlation with those kinds of tectonics?
So yeah, so this is, we looked, that's a paper that's right now under review. We've looked at, tried to separate oceans and cratons, for instance, and see if we can find some differences. And it's, the change in anisotropy at the transition zone seems to happen in the Pacific, mostly toward the older, mid to older ages. And then we do find some on, under cratons on average. This is still going on. Now, what I would like to do, in the near future is to try to get higher resolution models in the transition zone, and perhaps target, Pacific and target, for instance, beneath North America, see if we can resolve these differences, because it's hard to tell at this point whether we can resolve the differences in the model in the transition zone. We have a resolution of about 5,000 kilometers depth, so I don't know if there is a reason why it would be different beneath cratons or beneath oceans at those depths, but if it there might be some, we could learn something really good, very interesting. Yeah, if the water, if it's under subduction zones, which I cannot resolve, but if we find something specific to subduction zone, then maybe the water transportation could affect the anisotropy.
So Selwyn had his hand up, then Chris, then Alan.
I want to get some insight into the lifetime of anisotropy. I mean, you look at something and see paleo spreading, which of course happened a long time ago, and it's still remembering it.
Yeah.
And in other areas not. So when we see in a lot of the mantle, it's had a very varied history. So what anisotropy are we seeing? What dominates and how long does it last? Can it last for 100 million years? And can we create it very quickly with very high strain rate? I'm just wondering how much this obscures the pattern or complicates the pattern.
So it's been seen in several models that the seismic anisotropy in the lithosphere follows the paleo-spreading direction up to old ages. And so we assume they're related, but correlation doesn't mean that it's actually linked. So we assume that the anisotropy is caused by, it's following the spreading direction and it gets frozen and stays there. If there's no reheating event or nothing to strongly disturb the anisotropy, then we should be able to keep the signal frozen and still see it even
Then
with the
you
old.
go deeper and it follows the present spreading.
Excuse me.
If you go deeper, the anisotropy follows the present spreading.
Yes. Yeah.
So, whereas the little shallower, it follows the paleo spreading.
Yeah, because so if you take the oldest part of the Pacific and you look at where it follows the paleo-spreading direction, if you think you're going back in time, there is a point at which the paleo-spreading direction was the current plate motion, so they align, and so near the ridge it aligns with the plate motion, which becomes paleo-spreading direction, but then beneath that it remains the current plate motion.
It's a similar point, but I can't remember very well. But I thought on the Buckley you showed this, it was parallel and then became orthogonal. I thought that wasn't lined up with any, either current or paleo.
So in the middle of the plate, above 80 kilometers depth, basically, we don't find any alignment.
With any?
And no. And
How can that be?
I don't know. That's a good question. Except
It's historic. If the plate starts off, if it's lined up with direction at the time it's spreading, how can it change by?
well, so that's why
10 degrees?
we propose that it could be dehydration at the ridge, forming this chemical boundary, and so it's dry on top, and so it can't align with anything. It's too viscous, and then beneath it can align with the current plate motion, which becomes paleo-spreading direction, and so there's still this chemical boundary where we don't see any alignment above that with anything, but below it was able to align with the paleo-spreading direction.
Chris?
That's
So
how we
maybe
make
I've missed it, but do you see any effect of the Hawaiian flume?
No, Nick in his data does, it's enhanced discontinuity. With we don't have the lateral resolution of the model to see that small of a feature, but it probably does affect the anisotropy. I just can't see it.
So I have another question. Back to the question of anisotropy in the Mantle transition zone. You had on your slide that anhydrous ringwoodite is isotropic. But
Well-
what about hydrous ringwoodite?
So maybe I can go back to that
Because
slide.
the reason I'm saying that is because there's a paper coming out in Nature that will show a measurement on ringwoodite with about 4% water in it. And so my question is, if you have hydrous ringwoodite, would that?
Yeah, so Abby Kavanagh was showing in this paper that both hydrous and anhydrous ringwoodite are anisotropic, single crystal.
Okay.
But that if it's hydrous, then it aligns more easily with the flow, basically.
If it's hydrous?
Yeah, but This is the only paper on this, and Shankara Towatejiuga.
But there is a measurement being published on the 13th of May from Grant Pearson. It has 4% hydrous ring, 4% water in ringwoodite in a diamond.
Okay, well, I'll be,
So that's something that, you know, I'm interested in
yeah, I'll be curious
hearing
to
you
see
say
that.
whether that's gonna.
Break some embargo.
I think you can talk
Are you
about anything.
reviewer by any
We're not embargoed from talking.
But yeah, I'd be interested
But I didn't
in
say
seeing
anything that
that.
you guys can remember, right?
I'm genuinely interested because there's really not enough literature, and most mineral physicists don't think ringwoodite is anisotropic, so that kind of makes me wonder, are we actually resolving this, or is it just an artifact of the model? So that's something I want to look into, obviously, but if it's still there after we do even more tests, then this means something that must be coming from mineral physics.
Are there any other questions for Caroline? If not, let's thank her again for a lovely presentation.